So in the last class we talked about the basic CNN structure, that was the LXNet. Now LXNet was released, like we talked about, in 2012. So it was the greatest model at that time. But ImageNet competition keeps going on. So that means every time the competitors have to come with something better and better. So what happened in 2014 was the University of Oxford, they came up with an architecture or a model which was known as the VGG. So VGG stands for Visual Geometry Group. Okay, so this was released by the Oxford and we will be studying about VGG. Now before we go that, let us revise a bit about LXNet. So in LXNet, the very few things that you have to remember are, the main basics was it had 5 convolution layers and 3 fully connected layers, right? And the final layer, that is the output layer, had 1,000 1,000 neurons and MLP, which was softmax, right? And then the 5 convolution layer, initially they had 11 cross 11 filters, and then it was 7 cross 7 I suppose, then 5 cross 5, 3 cross 3, and it totally so the main task here was to increasing the size of the kernel, at the same time decreasing the height and the width, right? So this was the whole thing about LXNet, and we also had ReLUs and everything there. So now let us talk about VGG as a whole, right? So let us look at the architecture first. So this is a basic architecture of VGG. Okay, so here also the input is for 224 cross 224 cross 3. There it was 227, but yeah. So this is an RGB input. Here this is a very good photo of a car here. So this is where the input is. Then you have different convolution layers. Obviously the black one here represents convolution, which is followed by a ReLU, and the red is for max pooling, and finally you have 3 fully connected layers and a softmax one finally. Okay, so this is the whole structure. Obviously you have this is one convolution, this is second convolution layer. So what is the main difference that you can see here? In LXNet, what they had was, there was one convolution which was followed by one max pooling, then again convolution, and this went on until the very end, where what they did was they added 3 convolution and then one max pooling. Here this is a totally different thing. Here what they have done is, see, here you have one convolution which is followed immediately by another convolution, then we have a max pooling which decreases the dimensions. Now again you have 2 convolution layers. So what you can understand from here is basically that the convolution layers are one after the other. Okay, and so that means, if you remember, in LXNet padding was valid. Here padding will be same because the size remains constant for 2 convolutions continuously. Okay, now let us look more into it. So this is basically the structure of it, if you write it in this manner, obviously. So the first time what you have is the kernels keep increasing. Now see here, earlier it was 64, it becomes 128, then 256, 512, and so on. So one thing you need to know is, earlier when kernels were increasing, it was 96 or 358 or something like that. It was very randomly increasing. Now it is in the power of 2, so 2 to the power n, it is increasing in that format. See, so this is 2 to the power 6, then 2 to the power 7, 8, and so on. So okay, and the other thing about this is, like I mentioned, VGG itself has different different layers. So you have VGG, small VGGs like VGG 11, you have VGG 13, then 16, and then finally 19. 11 and 13 are not used a lot. It is usually 16 and 19 that are used a lot. Okay, so then you have pooling. So obviously this is max pooling, and this just basically is used to decrease the dimension of the height and width and increasing the kernel size at the same time. Okay, now these are some of the most basic differences that you can see. Now let us look into more depth what other difference there is between VGG and LXNet, and why VGG covers in places where AlexNet failed and what were the failures. We will go into all of these in details. Okay, so here you have another structure. Okay, so here first you have the image and this is followed by 2 convolutions. Here the feature map is 64, that means you have 64 kernels and the kernel size is 3 cross 3. So that basically brings it to 224 cross 224 cross 64. Again the padding here is same. So you need to actually understand what is happening. So the padding always remains the same. Now this is followed by a max pooling. Feature map remains the same obviously. So max pooling, the stride is 2, so it basically halves the whole thing and it is 112 cross 112. Activation, everything is ReLU except the final softmax which is in the final output layer. Okay. So one thing that there is when whatever be the VGG, this is this part, these 3 layers will always remain constant. Okay, so these fully connected layers are always there in whatever be the VGG, VGG 11 or VGG 13 or VGG 16 or 19. These 3 layers remain the same. So you always have 2 layers of 4096 units or neurons followed by 1000 layer. Okay, now you can see here this is basically the structure that was given in the paper. So these are different models of VGG. So VGG 11, 2 different VGG 11s, then you have VGG 13, 216 and 119. Now let us look in the difference. First of all, one more thing that you might have noticed, it does not have very large kernels. If you remember what we did in AlexNet, we had 11 cross 11, 5 cross 5, all these big size kernels, right? But here all the kernel are very small size. So why is that? So one thing is that as the model size increases, as the number of layers increase, the number of parameters keep on increasing. AlexNet has what, 60 million parameters? But the problem is we need to find an efficient way where we can increase the number of layers or increase the depth, but at the same time we do not increase the parameters by a lot. So that is why what they have done is they have found a very nice way to find this kernel size. So what they did is they found out that instead of using one 5 cross 5 layer, we can use 2 3 cross 3 layers. So the output is the same thing. Okay, the output is not changing. The 5 cross 5 is very equivalent to 2 3 cross 3 layers, but these 2 3 cross 3 layers, they actually reduce the number of parameters. How? Okay, let us look here. Let's say we have input and output C channels. Okay, so we have C channels now and you have 2 3 cross 3 into C cross C. That means if you have C channels and 3 cross 3 is your kernel size and you are using 2 kernels, obviously 2 3 cross 3 one after the other convolution, so these will be the number of parameters in that case. And now let us look about 1 5 cross 5 cross C cross 3. This is one convolution. These are the number of parameters that will be required for one convolution when 5 cross 5 is the size of the kernel, right? So now let us calculate what happens here. 3 cross 3, 9, 9 2s are 18. So 18 into C cross C. And here what will happen is 25 into C cross C. So you can see here this actually decreased by a lot. Now if our C is less, it won't matter a lot, but if our C is more, so if you have seen here, these are number of kernels, so 128, 256, 512. So if this is even, let's say 128, so this becomes 128 cross 128. You realize how many times difference there is. So that is why what they have done is they found out through experimentation that one 5 cross 5 kernel can be replaced by 2 3 cross 3. So what they do here, that is why, is instead of using in AlexNet, what they did was they had one here and one, this was followed by one 5 cross 5 convolution. Here what they did is instead of doing that, they are using 2 3 cross 3. Now this output is again passed through a 3 cross 3. Okay, are you getting the idea? So that is why you have 2 one after the other, 3 one after the other, followed in the middle one pooling. This can easily be replaced by one convolution if the number of kernels is 5 cross 5. Okay. So now let us look here. So we have 11 layers. Convolutions are there, 3 cross 3 convolutions you can see, and then 256 is the number of kernels. So this goes on. 11 is not used a lot. Here you have the same thing, 11, but this has the local normalization like I was talking about in AlexNet also. So local normalization is not a very big thing. It was back then, but later on it was realized that it is not used a lot, and since we need to keep changing as well, so we dropped out about local normalizations and we do not talk about it that much. So these both are the same thing, except the difference here is local normalization. Then we have 13 weights. For 13, what they have done is they have added some extra layers here. You can see instead of one convolution they have followed 2 convolutions. Now they have this C and D, they both are 16 layers. Now in 16 layers what happens is everything is the same here except the dark part. So here what they have done is they have used 3 cross 3 kernel and 256 number of kernels. Here they have used 1 cross 1. I'll talk about this 1 cross 1 also, it is very interesting, but let us come to this slowly. So again here 2 3 cross 3 and 1 cross 1, here you have 3. So the whole thing, if you see the final 3 layers that I was talking about is the same. You have 3 fully connected layers and 1 softmax layer. They are going to remain the same. Everything else above, they keep changing. These 3 are constant. Okay. Then you have finally 19 layer weight. So you have these 3. By the way, this was to make VGG16. It was trained for 2 weeks on NVIDIA Titan GPU. So it is a lot. And okay, so I know these two. This 16 weight, it took 134 million, and here it was 138 million. Now the difference here is, see, you have convolution 1 cross 1 kernel, here 3 cross 3 kernels. So this thing, basically these 2 layers reduced 4 million in number of training parameters. Now can you understand the problem that was happening? Okay, so after this, finally this whole thing is alright. So you understood this part. Now let us talk about something else. So let us talk about this 1 cross 1. So this 1 cross 1 kernels were added to decrease the number of parameters without actually changing the shape or the width of the kernel. So this is basically the whole thing, the whole input size is equal to the output size, but the number of parameters decrease. So that is why 1 cross 1 was used a lot. And yeah, this is also used to increase non-linearity. See, if you are using ReLU, there is a very big chance, and also you are using convolution. So convolution is basically what it adds more linearity to the thing. You just have multiplication followed by addition. So addition is basically linearity. So there is nothing there. So to add more non-linearity, we use 1 cross 1 kernels. Finally, let us talk about how it was trained. Training part. Let us come to that. So in training, what they did is, for optimizer, they used SGD with momentum, and the momentum is of 0.9. They used a batch size. The batch size for training was 256. The regularization they used was L2 regularizer. So they used L2 regularizer, but at the same time they used dropout as well, and the dropout value is 0.5. So 50% of the neurons were removed at any training epoch randomly. Finally, let us look why VGG was better than AlexNet. So first of all, VGG got more accuracy than AlexNet. The first thing, obviously. Second is, VGG helped us show how we could optimize the model. So that means VGG increased and showed us how we could increase the layers without actually without increasing parameters by a lot. So this was actually a very big thing because you need to optimize it a lot. Number of parameters are going to keep increasing, so you need to make sure what is happening. Like here, so they found out a very good technique. So here what they did is they used kernels, small kernels instead of bigger kernels, and they found out how these small kernels were very close and gave very pretty accurate results, but at the same time they reduced the number of the number of parameters that were required to train. And finally, the weights were initialized normally and the weights lied between 0 and 0.01. The biases, they were all set to 0. They were set to 0, but obviously with training they change. But this was the initial way how they have set. So initially the weights were set to a normal distribution which lied between 0 and 0.01, and biases were set to 0. So this is the whole thing about VGG16. So the big thing that to take from here is, first of all, it increased the accuracy. It helped us go deeper into the models. One thing you need to know is, as the number of layers increase, there is a very big chance that your accuracy is going to increase. But with AlexNet, it was difficult to go deeper. The reason was obviously that AlexNet did not have any optimization techniques. They used very big kernels and everything. So in that case, this actually wins by a lot. That is the whole thing with VGG. Obviously, it still took a lot of time, but this was a very deep network when you compare to AlexNet, and it was a very big thing back in 2014. It also gave a very good structure if you see. So it starts with 224 and then it drops one by one. It just goes half, so it's easy pretty much to learn, and the feature maps also increase in the power of 2. So that's it, and in the next class what we will learn about is InceptionNet. Okay, so that's it for today. Meet you next day and keep learning.